All right. Okay, and we should be live here now. Okay. All right, well, welcome back. We are now recording live on YouTube. I'd like to introduce our second hour here, and I'm going to get the share screen mode here going. There we go. This is a presentation that to me, I was excited when Gordon told me about it. And I said, oh, you're going to present that? That's awesome. And it's going to be on the Sbitx radio. You're really going to like that. So how many of you have heard of the Sbitx radio? I just bought one about in Christmas time. I've got one now, but I was a little disappointed when it wasn't a full kit to put together. I thought, oh man, I thought I was going to get a full kit to put together because I actually enjoy surface mount soldering. Yes, I actually do. But the Sbitx, I mean, that's an analog design the transceiver. I'm not going to steal any Gordon's thunder. I'm going to let him tell you all about it. And I think you will enjoy the program, and I'm going to get your slideshow started and let you take it away. F5 is your friend. Yeah, well, I've tried that earlier and that didn't work so well. So I'm trying to see so you can see your video pan here. And thumbnail here. There we go. Now you can actually see your view there. And so you can adjust the lid for your camera and take it away.
Morning. So I'm retired. Oh, it's such a great feeling. Why did I agree to teach high school in retirement? Work harder than I ever worked. I'm up at 4:30 or 5. Taught a year of calculus in 3 quarters. We're ready for the calculus BC test. Almost finished physics 1, which is supposed to be a year, but we did it in 2 quarters. Now we're halfway through physics 2, which is supposed to be a year, but we're going to do it in 2 quarters. And I got 2 students that are doing excellent at that stuff, which is why I don't get much sleep, because I have to do all the same homework. I haven't done calculus since 12 years ago, and I've never done BC calculus since 45 years ago at Georgia Tech. So I can finally integrate, differentiate, do infinite series. I know L'Hopital's rule. I know all the buzzwords, and most of them I can actually do. In physics, that's a little easier for me, but it's a lot harder for the students. And then I have 8th graders. 4 of them are failing. It's really sad. At any rate, so I get to work with the best. We're going to be the brightest of our nation in the future. And I get with folks, I tell them honestly, if you're not going to learn what I'm teaching you here in 8th grade, I have some recommendations. Jog a lot. Get really good at shooting and learn how to use a shovel, because that's what the Army or the Marines will have you do. So at any rate, I caught a cold or something on Tuesday and I was sick as squat. I had to miss 1 day of school. Too sick to even teach over Zoom. And then the fever finally broke and I'm still coughing up crud, but the COVID tests were all negative. So I assume I had the flu or something. I'm still coughing up all kind of junk from my lungs, but I haven't had any fever. So as far as I can tell, I'm relatively safe, although I'd recommend you not get too close. I practice medicine still. I practice about every other Monday night at a homeless shelter, giving away medical care for free, and it's worth about what you paid for it. I see Mike Hasselbeck is in the group listening on Zoom. Boy, he has taught me so much. Mike is a real physics professor, and he really knows how to do some of the stuff that I only play at. So he helps out a lot. I did these slides on cheapy stuff because I refused to pay Microsoft money. So I hope that they present on this newfangled whatever he's got here. We'll see.
They'll be on the section website after the conference.
So I can see right off the bat that all of the formatting doesn't work right between Microsoft and Open LibreOffice, but that's life. So I brought a picture. You'll see why in a minute. Of the Sbitx. It's a really wild radio. It's been 2 years or so in the making. Lots of delays. COVID didn't help. SDR architecture. Man, the PowerPoint really screws up everything. All the modulation, demodulation is done in software. It's a Raspberry Pi 4 processor, or it was. Touch screen, which turns out to be like commercial. Like I discovered you can just buy them. Any mode that you can mathematically define, it can do. So it can do native FTA, it could do native FM, it could do native, anything that you can mathematically describe. So Osher built in FTA, built in PSK31. It's anywhere from 10 watts to 40 watts, depending on what band and how hard you like to push $1 transistors. The digital filtering it's beyond anything I've ever seen. It makes the 7300 look clunky. It is so much easier to use. I don't think I have a pointer here, but on that upper part where you see the little box above the waterfall, you just grab the right side of that and shove the filter over. Grab the left side, shove it wherever you want it. You can make the filter be whatever you want. It is so much nicer than a 7300 in that one regard. Osher and I worked together on a ventilator for third world countries, or maybe even the USA. We made way too complicated a ventilator. We made an ICU ventilator running on our Arduino. The FDA was not ready for that. So we never made it through the emergency approval process. What they were looking for were things with bag squeezers and stepper motors. And we delivered a time cycled pump system that would do PEEP, would do any kind of assisted ventilation you could think of. It was way beyond what we should have tried to develop. But in the process, I got to know Osher reasonably well. Osher apparently runs a VoIP telephone company in India, one of the first. And I think he's independently wealthy. Oh, I really don't know. But he and I were desperately trying to solve some technical problems at the beginning of the ventilator development. And I had his phone number, but that is not something I do. I don't just call India. And we're off by 12 hours. So he works in the night and I work in the day, and we would go back and forth. And I need to talk to you. He said, over something called Google hookups, which I hate. What's your phone number? So I gave him a phone number. Bring, my phone rings. It's Osher. Like, how'd you do that? He said, that's easy. Anyway, so Osher is a very interesting dude. He has his strengths and his weaknesses. So I'm going to try to show you some of them. So Osher gave a talk in 2021 where he explained how this radio was going to be built. And I haven't actually watched the whole talk, but I've watched enough to know that it was really, really a fascinating radio. Again, do you guys have a pointer anywhere here? I have a weak one. It's very, very weak. But they use the Raspberry Pi. The Raspberry Pi controls a WM8731 codec. It's the thing that is inside your CD player that goes to your headphones and produces the audio. And it also has a microphone thing, and it even does the bias for the electric microphone. And it's got all kinds of amplifiers in it, and A to D and D to A. And I don't know how many bits it is, 12 or 24. I have no idea. But it's fast as lightning. And it can, I'm sorry?
Is your non-contact, I believe?
The
thermometer.
Hey, you know, I didn't think
That's
about
not
that.
laser.
Oh, so there's the codec right there. And that thing does all the sampling. Your screen is 19.7 degrees Celsius. I had to teach this to 8th graders this week. It was the AP physics students got it about 3 months ago. It's the same stuff. I just water it down. They don't know. And then once you generate the signal, it goes into some amplifiers and da 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 da. So the big deal between this and a 7300 is very, very simple. The 7300 has FPGAs, which I think stands for floating point gate arrays, but I'm not really sure. Oh, well, whatever. But they're expensive and they do cool stuff. Osher doesn't have them. So they can generate RF on the fly. at really RF frequencies. Osher can't do that. So what Osher had to do was generate the RF at 24 kilohertz. That's his low IF, is 24 kilohertz. So it's ultrasonic. And then he has to heterodyne it up and up and up to get it to where he wants. And that's where the problem came from. So the 7300 can digitize at full speed HF communications, just digitize the RF and then use a digital filter to pick what it wants to look at. Osher can't do that. So he digitizes at 96 kilosamples per second, which gives him plenty of ability to grab all of the signals at an IF of 24 kilohertz. And he can grab like a 50 kilohertz wide IF and digitize the whole thing. And if I understand right, he's digitizing and performing FFTs. The digitization is at 96 kilohertz and the FFTs are at 10 milliseconds. But I haven't ever even gotten into that part of his code. So I can't tell you that for sure. But all of this stuff up here, this is basically 3/4 of a micro-Sbitx. That's all it is on a little bit of steroids. And I think he says you could build this part for $100. So it's just like 2N3904 transistors and 2N22s. And he's got a little bit fancier MOSFET at the output, so he gets higher output. And unfortunately, this is where the problems are. This part's dirt cheap. That codec is $4. $4. Hello, 7300. This is your competition. So the real problem that Osher had was because of some of our exalted leadership in government, they killed the supply chain, killed it. I had people evading the police to build ventilators. That's in University of Florida. We had to sneak around to evade the campus police to get our measurements and our labs done. At any rate, so the Raspberry Pis were almost unobtainable. And he finally managed to get his hands on some Raspberry Pis. The scalpers are the only people you can get it from right now. The authorized resellers have zero stock whatsoever. So we're all having to use crappy hardware now because they destroyed the productive capabilities of the silicon chain. It's just insane what happened. So at any rate, when he first gave this talk, the IF was going to be at 27 megahertz. Osher is famous for taking 10-cent crystals and making a $300 radio out of them. But he moved it to 40 megahertz to avoid some image problems. And so that's what became the final product, was 40 megahertz. How does this work? Okay, so I already told you some of this stuff. 7300 proprietary software, 100 watts, extremely clean. Oh gosh, they're clean. And direct RF frequency demodulation, that's $4 signs. The Sbitx open source software is Smash. I download the software. I edit the software. Anything I want, I can do. 40 watts at best. It will do more, but you'll burn some stuff up. Declines to 10 at 10 meters. An iffy system. Yeah, it turned out. $500 was the purchase price, and we had to wait because there were no raspberries. So I already told you how this works. I already told you how that worked. Okay, well, I see PowerPoint's done it to me again. Internet forum, the hundreds and hundreds of people are contributing to this forum. You can subscribe to it. It services many different radios. The topics for ours are under headings like Sbitx. So here's the top, the speaker. And then I've lost screws already. So I got the left side off. The first thing I did, might have been part of the problem, was I said, I've got a lot of money invested in this thing. I do not want somebody plugging in the wrong power supply and blow the living daylights out of this thing, because that's happened with gear in our neighborhood. So I put a polarity protector that I designed one of our circuit boards. I can't drill straight, so the holes don't match up. Camera's on the edge of the laptop.
Lid. There you go.
There you go. So this is our circuit board for a polarity protector, and I had that installed in here because I had $500 wrapped up in this crazy little piece of equipment. So Allison, a retired RF engineer who has been just absolutely fantastic for all of us, told me the trick, or told us the trick for how to get this thing apart without having to absolutely dismantle everything. So I have marked the screws that have to come out to get it mostly apart. Because every little deadgum thing that I ever had to do with it, I had to disassemble it. And I've already lost enough screws. So Osher's really good at making circuit boards. I am less good. Oh, I forgot. This got to run through. You'll learn more about this. Okay. I'm still stuck. What am I stuck? Well, let's just go this way. Let's go that way. All right. So this is the digital pipe. Is off the shelf, except for this circuit board right here. There's a little bitty circuit board, but that's a Raspberry Pi, and that's a DSI ribbon cable. And I sure wished I could find out where to buy those, because mine I've just about busted. And then he's got this little analog gizmo here to read the front panels. And then this is apparently a camera. This is a camera. This is a stock standard 7-inch touchscreen. Works great, and it's really pretty too, by the way, much better than the 7300. And then I don't know much about this display, but you can buy them for $70, I discovered, so they're cheap. And this board here, this is the only important part of this. This thing's got the codec on it. That's the codec right there. And it's got a couple of transistors and some resistors. And that's it. I mean, I could even lay out that board. So this is the entire digital transmitter receiver. And this is the rest. And here's where the problem is. So this is the analog radio. So it's got the 40 megahertz, the filter. It's a 30 or 40 kilohertz wide crystal filter. It's just the IF filter. But that allows him to have a pan adapter display that's constant, always available. You can decide how wide you want it to be. Now, these are hand-wound toroids. These are hand-wound toroids. And this is the RF part of it. Okay, so here are the final MOSFETs right here and right here. And there used to be this little linear regulator used to be underneath that bar. Osher likes to push components. So he couldn't use insulators to hold the chips onto. This is a nice heat sink, but it would melt the insulators. So he had to use a metal bar to hold them down. I'm like, oh gosh, what are you doing? So he was blowing finals like popcorn. And I was busy teaching high school, so I just didn't turn the radio on. And whenever I did, I used a little 2-amp wall wart that wouldn't blow up anything. And so I managed not to blow my radio up while other people figured out what was going on. And this was what was going on. That's the oscillation. At some VHF frequency, 100 watts was being developed every time it flipped from transmit to receive. That wasn't so bad. What was bad was it was developing 20 volts RMS on the gates of those final MOSFETs, which are only $1 each, but they're a pain in the butt to unsolder and get out of there. And it was blowing the gates because it exceeded the voltage that the gate insulation silicon dioxide was built for. So they came up with a Bandaid. They had you cut a trace, change the timing to try to sequence what stages got voltage in what order. That allowed them to get rid of the analog power supply and switch to a digital switching supply, which I don't have here right now. which would stick up in the air, and then they could get the bar to lay flat because they were afraid that the transistors weren't laying flat. So I never did that mod. I was too busy. And I said, I think I'll wait. Good move, because they kept blowing finals. Then the real problem of the oscillation was discovered. So that is the transmitter output. This is a switch right here. It's a relay. There's a gain stage, which I think is a BFR 106. Another gain stage, which was 2 and 2222s. That's an IRF 510 gauge stage. And here's the final, is it IRFZ 224N or something like that. There was enough capacitance across the read relay that it coupled the output to the input of the whole amplifier chain. And the amplifier chain with 1, 2, 3, 4 stages had enough gain that the whole thing could oscillate. And that was what was killing him. So a long discussion began of how are we going to fix that? And there were a lot of crazy ideas discussed. But then they began to talk about solid state TR switching. And at that point, I got really excited. I haven't had a rig that could do that kind of switching since I was in the 10th grade at Sylvan Hills High School and had an HW16 that could switch instantly between dots and dashes. So I bought one on eBay. It's sitting at home waiting for me to repair. And then they started talking about solid state switching with the Sbitx. And I'm all over it. So this is a chance, because Osher builds crappy CW rigs. This is a chance for Osher to build the best CW rig in the world at this price point. He'll compete with Elecrafts. He's using the intrinsic layer of the 1N4007 high voltage rectifier. I had no idea how this worked. So it turns out the deal is you start these carriers, these holes or electrons, whatever, and they move into the intrinsic layer that's between the P and the N layer, and they kind of like hang out for a little bit. And you can shut things off, but they're still there. And so if your RF is fast enough, and according to the RF people, 2 megahertz is as low as you can go, but above 2 megahertz, there's enough drift time in the intrinsic layer that you can still conduct RF right through the diode if it's forward biased, even on the reverse cycle of the RF. I'm like, wow. And so if you want to conduct high power, you need like an amp of DC, but if all you need to do is conduct the receiver current, 50 milliamps, turn the diode on and it conducts RF. Turn the diode off, nothing. So this is an astonishing switch for RF, and they're 10 cents each. So I think I got the name right, Hans Summers, who I think may have done the QDX and has done a bunch of other really cool radios, is friends with Osher, as is everybody, and gave him hints. And this is the circuit of the TR switch. I'm going to briefly show you how it works. So let's see. Those are the diodes, 1N4007s. I think MFJ had a product that was like this. I haven't torn into the one that I bought off eBay, but I bet it works the same way. And all he does is provide DC bias through a coil and a resistor, DC bias here, DC bias, and he flips what's turned on and what's not turned on with MOSFETs. And that's how he operates this. This is really cool. These are diodes to protect the input of the receiver. This is additional. This is a series pass and a shunt MOSFET to short out and open up and provide additional isolation between the transmitter and the receiver. And literally, you connect this 100% of the time to the transmitter output. And then this switches whether or not the receiver gets to see it. So how many of you have ever tuned a duplexer at VHF, UHF? Now you understand this. This is 70 dB or more of isolation. So the cool part of what Osher did, and I'm sure this was Hans Summers' design, instead of having a honking big RF voltage supply, he simply used a voltage doubler from the RF itself to develop the back bias. Wow. Whenever it needs it, it develops back bias, and it will always develop enough back bias because it is voltage doubling the RF that it got applied to it. The only crappy part was it doesn't have enough 1N4148s to handle a 7300s output. So I got to build my own little thing so I can make this thing switch better. And then I can take a micro Sbitx and put this thing on it and run my 7300 transmitter and have full break-in CW with a micro Sbitx as my receiver. And I'll use cat control to read the frequency and then program the Arduino to make it be on the same frequency. I might have a lot of fun. Anyway, so I thought this is the coolest thing I've ever seen. I've never seen such a device this cheap, and I want to show you that circuit. So that circuit is right here. That little bitty board, that's it. That's the solid state TR switch. The little bitty thing right there. And so I got real excited. Okay, so then they sent us the second upgrade package, and now I started to pay attention. And it included a spare set of transistors, new transistors to change out the 2N222 stage to 2N219s. I didn't know this. It's the same die. It's just a bigger case, and so it can dissipate a little bit more energy. They had people reverse trace cuts they'd made, but I never made the trace cuts, so I didn't have to reverse them. Provided the new solid state TR, and an enormous document. Oh my gosh, downloading that thing on how to install it. They had problems mailing it. They had problems getting parts. They had every problem you can think of. And finally it arrived, and I'm not that good at SMD soldering. I'm using a itty bitty little USB-C soldering iron because it's all I got. And I managed to replace the 4 transistors. I managed to cut out the IRF 410s. I put in the traces. There were several little resistors that I had to replace. Oh, mine are sad. And then I soldered in this box. And there is the switching adapter that we put in to replace the LM309K linear 5-volt supply. So I told you that I put in my MOSFET P-channel power protector. Again, PowerPoint has sent me in. But that's basically what they look like. And when I got this thing going, I was like, oh, that driver stage, I accidentally touched one of the transistors, burned my finger. I'm like, is this safe? So I calculated he was running the junctions up near 150 C. They're rated to 175. That's closer than I want to get. So I complained and I tried to change the biasing, but Osher cautioned that he needed that to reduce the IMD. What? Well, he's right. You can see it on the spectrum analyzer. As they warm up, they get better. This is a weird design, folks. So then I made a modification to the simple audio circuit because somebody said I needed more treble. Well, that wasn't really my problem. I had many other problems. That wasn't it. But I added a capacitor here, and as a result, I provided a capacitive shunt around the biasing resistor, and the next thing you know, I'm blowing 3904s right and left. So I changed it to 0.1, and that fixed it. And then I made the mistake of connecting it to a spectrum analyzer. Well, I had this resisted tap on my Heathkit antenna that's 60 years old, and my signal was about -10 dB. So legal would be -53, and there was a spur at 18 megahertz. It was 6 dB over the limit. A spur at 10 megahertz, it's 3 dB over the limit. A spur at 12 megahertz, that's 2 dB over the limit. And a signal at 16 that's right at the limit. And I hadn't even looked at the low end yet. So I started a thread on groups.io that now has over 260 posts because this isn't legal. This is a problem. And why is this? And we had to figure this out. So I started looking at every part because you can touch these collectors. These collectors are metal cans, so you can make a modified scope probe and you can actually touch them and get the collector signal. And this thing scares the daylights out of me. I mean, you could drop something in here and just blow up all kind of stuff. I had to wrap my voltmeter probes because I didn't dare short two things out inside this thing. I never figure out what I blew. So here's the signal at the pre-driver stage, and that's not so bad. Well, there's a second harmonic, but see, there's no low pass filter at this level, right? So that's okay because that's going to get fixed by the low pass filter at the end. But there's still already spurs showing up. So this signal was created at 26 megahertz, 24 kilohertz. It was heterodyned to an IF frequency of 40 megahertz with an SI5351 oscillator square wave signal. And then it got filtered, and then it got heterodyned with a 54 megahertz signal from the SI5351 to create the 14 megahertz 20 meter signal. And that's what I'm looking at. We're now just in analog circuitry where I actually know what I'm doing, and that's not terrible. But that's what it looks like when you get to the drivers. Oh my gosh, those things that were burning my fingers. There's more spurs there than I have grandchildren. So this is terrible. And there's a 2 megahertz spur. What's that doing there? So I was a little beside myself. So the spurs are just everywhere. So then I went to 75 meters because there's a net that I wanted to get on. And I looked at the 75, and there's these giant spurs around 75 megahertz that are 520 kilohertz below and 520 kilohertz above. And like, what in this radio is making 520 kilohertz? So I had no idea. And we did every subtraction and addition, 3 of this, 5 of that, subtract, add, whatever. So I gave up and I used a Heath kit. I ran it through an SB200 amplifier, cleaned it up just great. Good old tuned circuits in the SB200 with 572Bs. And now I'm on the air and I'm legal. Lots of output too now because 40 watts and 7 dB gain. So, but this is a sad way to have to run an SDR radio, clean it up with a vacuum tube. So, well, is it the mixer? So he has this fancy mixer on the second stage that's actually a single pole double throw solid state switch. It's called a commutating mixer. And so it has perfect isolation between one input and the other. And then past that, there's not as much isolation, but there's a zero crossing point. It's like designing an op amp. You have to pick the what is the reference voltage. And he had a pot, RV2. It's right here. And you set the zero crossing detector point with RV2. I discovered that made a big difference. So I'm all about changing RV2 and just trying to get this down. Osher pushes all of his transistors because he's trying to design stuff cheap. So he's using transistors that have an F sub T of only 300 megahertz. Theoretically, their gain goes to unity at 300 megahertz. So theoretically, at 30 megahertz, their gain's only 10 dB at best. And that doesn't leave you much room for negative feedback. So he's pushing all of his transistors with minimal negative feedback. And I wanted to change that, add more linearizing gain to some of these stages. I never got to that. So I tried shielding. I built this little shield out of aluminum, and I tried to shield the mixer stage where I thought some of the stuff might be entering. It didn't do squat. I did something. Osher's a pretty busy guy, so he asked me to make a couple of tests. I disconnected the amplifier by simply removing C5. And then I looked at the signals, and I don't remember what all these are. I think this one is 20 meters. Look how beautiful that is. There's nothing. It's completely clean. That's what's coming out of the mixer. But if you add the amplifier to it, it just gets destroyed. That is the 80 meter signal, and I'm looking down here into the mud. This is so clean. These are real signals, but they're way down there. But it gets worse and worse and worse as you add more stages. So I think I already did that. So I worked for weeks making plots, running things, trying to fix any of these problems. Can I get these spurs down? Osher did not seem to understand this is serious. Apparently he hasn't seen this. Most of his radios work, and we were having a hell of a time. So the first mixer mixes with 40 megahertz. I already told you about how some of this stuff works. We found the explanation for the 520 kilohertz. That's the switching frequency of the switcher that he sent us to add in. So the 5-volt supply was creating 520 kilohertz square waves. And I believe it's creating them on the plus 12 volt input side because it's oscillating how fast it takes power from its input side. Those are inadequately filtered at the pre-driver driver stages. And that's how the modulation is happening, we believe. So I built an external power supply that's sitting on beside the SB200 amplifier, and that's an LM309K, and I rigged that thing up so I could run my radio. So now I got wires going out to run the 5-volt side of the thing. I'm scared to death I'm gonna blow this thing to kingdom come. And I got rid of that. And then Osher did some tests that demonstrated that the SI5351 chip, which has 3 oscillator outputs, literally had crosstalk between the outputs. Now, this had been known from the micro-Sbitx stage, but it was coming around to bite us again. So the cure for that is to get 2 SI5351s and use 1 for each, right? Well, that's a little hard to do. So the first thing he did was he said, reduce this capacitor from 0.1 microfarads to 2.2 picofarads. That's quite a reduction, folks. And then he changed these resistors. This is an emitter follower stage here, just as so this adds isolation, and this reduces the current that the drivers inside the chip have to do. And the other stage is simply a semiconductor switch, and it draws almost no power. So this is the best you can do to reduce drive. So when we did that, we got rid of some of the problem, but that 2 megahertz spur is still there and still making us illegal. So I didn't have any other way to add a second SI5351 than to take one of my homemade VFOs with a Raduino from the micro-Sbitx days. This will drive an SB102, by the way. You can computer control a Heathkit SB102 with this little gizmo made in a thrift store bread pan. Really good shielding. And that's where I got my second 5351. And I wrote code to put that on 40 megahertz. And then you just connect this up and bingo. I now have 2 SI5351s. One's doing 40 megahertz, the other's doing 54 megahertz. And that's the best I could do. So now I'm running 2 radios and 2 power supplies and trying to keep this silly thing going and trying to reduce these spurs. At that point, my output started to get flaky. It would be 20 watts and then a quarter of a watt, 20 watts, quarter of a watt. So it's really hard to run tests. So when I started probing around, it turned out to be a flaky soldering joint right there. And when I touched the soldering iron to the drain of one of the IRF Z24 whatever's, it fixed it. So in all of my machinations, that joint was either never properly soldered or got broken, but that fixed that. So the driver stage was such a disaster. I didn't know what to do, so I used infrared temperature measurements on each transistor to see what's getting hot. And one of them was 6 degrees hotter than another one. So I had a supply of these things, and with a little bit of effort, I managed to get them slightly better matched because there's just not enough negative feedback in that stage. And I got a significant improvement by just doing that. Then another guy said, well, change the bias on them because it's getting crappy bias. So I built a small filtering system right here to filter these things. I don't know if you guys know it, but you buy these components from Amazon, and this is $10 worth of resistors, and it's like a penny each. It's unreal. And these are my capacitors. So if I need a capacitor, I got hundreds of them for $10. So I was like, oh, there are some advantages to this. So this afternoon, I'll be talking about taking advantage of that. At any rate, so then I made this radio legal. I was so happy it lasted for 24 hours. But I literally had this radio better than legal, and I could actually run this radio. And I kept good pictures of all this. What do I do here? And then I moved the 5-volt supply back inside. There it is right there. Same supply. All I did was transfer it back inside. And the next thing you know, it worked for a few minutes and the display went dead. The Raspberry 4 went dead. That's a pricey little piece of gear. Well, I had a backup Raspberry 4. So I carefully measured the supply voltage. It was perfect. Carefully checked all the communication. Everything was perfect. And I took my only last Raspberry Pi on this planet and plugged it in, and it blew immediately. So that was it. I no longer have a radio. All my efforts are toast, and I got to wait and see if anybody else figures this out. So I was a little pissed. So I want to discuss some of the trade-offs and then tell you what has been discovered. So having more stages would have allowed Osher to have more linearizing negative feedback, but it increases the complexity, and as he had discovered the hard way, increases the chance for feedback if you use relays, and relays don't offer the best isolation. Osher tends towards the highest gains per stage, and so he runs into problems with IMD problems because he's not trying to build a 7300. He's trying to build a radio for the third world. And so it's a slightly different design goal. Allison, by contrast, designed the amplifier for QRP Labs, and she's just horrified at Osher's designs because her designs run 10 watts output flat. His isn't anywhere close to flat, from 2 to 30 megahertz using a 12-volt supply. If you put a 20-volt supply on it, you can get 20 watts out of these things, 10 watts clean at 12, 20 watts clean at 20. Two-stage amplifier provides 26 dB of gain. She ripped all this stuff out, put in her amplifier as soon as she got her hands on it, and I'm sure she had a lot less trouble than I did. The delivered boards don't even match the schematic. It's changing so fast. Osher's not good at keeping the schematic updated. So there's a transistor on the bottom of this thing that's not on the schematic. It's soldered to the bottom side. And some people had to add a RC component to that to make it switch properly. Osher had me add a capacitor in series and a resistive termination for one of the filters to try to improve the filter performance. But there was already a resistor there. It wasn't on the schematic. None of us knew it was there. So I had to try both versions, with and without. And so it was a little, there's no component layout published. There's no trace layout published. So I had to take an ohm meter and try to mark what do some of these traces do to try to make sure what am I connecting to. So I'm pretty good at scraping onto these things and soldering connections to these things. I didn't tell you, but we have managed to reincorporate the reed relay. So we have not only the solid state isolation, but we also have the reed relay isolation to give us even more isolation between the receiver and the transmitter. That appeared to work, but I would have tested it without, but I don't have a radio anymore. Lack of clear explanation of how to find libraries. So trying to recompile this can be a problem. You need to sort of be a Linux guru to stay up on this stuff, and I'm not. I know just enough to be dangerous. Lack of trace layouts, lack of benchmark spectrum analyzer plots, testing the extremes of component survivability as well as my fingertips, the edge of component gain linearity, and none of us know it might work with a 3B plus. which I've got some at home, but I'm not willing to sacrifice quite yet. I got to figure out what is going on. He has an amazing willingness to provide upgrade products. I mean, shipped from India to every single person who bought the development edition, extra transistors, full extra. This wasn't promised at all. This was out of his generosity. We got these upgrade kits with full instructions of how to do it. I mean, that's amazing customer support to match his incredibly poor ability to keep the schematic up to date. And all the code is available. So it's a mixed bag, and it's definitely a crowd development. And then along came Evan. Evan Hand stuck a capacitor, a 3300 microfarad capacitor on the 12-volt line after my radio was kaput, and it got rid of the 520 kilohertz spurs. So he found a way to fix it that nobody had. He just said, well, why don't I try this? And it worked. So this makes us think that the 12-volt filtering on this radio is suspect. And that provides amazing feedback opportunities and IMD opportunities everywhere. And so if I had the radio working, I would be testing those theories. And this is Evan's output, and I can't count all this, but 10, 20, 30, 40, this radio is thoroughly legal. His only problem is he's got a minor problem, I think, on the second or third harmonic. It's just a dB or two, and he thinks a tweak of the low pass filter would fix that. But Evan's got great results. And so there's hope that they'll fix this. So why is mine so crappy? Osher has several times said, Gordon, I have no idea why yours is so poor, because, you know, ours seem to work. And I'm like, yeah, but you're manufacturing this product variability. You got to fix this. You got to find this. Okay. So I have a suspicion. What I think Osher didn't know about was how sensitive his product was to wires and wiring and lead dress. I have a small semiconductor switch to allow me to turn the SP200 on and off. Once I ran that line simply from here to here, and I had spurs out the wazoo, because that line is connected to a line that controls the +12 switching for transmit and receive. That's a sensitive line. So I put it inside coax and ran it all the way around. But I think his 12-volt system is incredibly crucial to the purity of this radio. And I had this power protector right here with 12-volt wiring sitting up here connecting to his switch, which he put the switch up here and all this 12-volt wiring right here, which you can see I have now wrapped with a ground wire as a simple shield. So I think this may be the cause of my problems and potentially other people's problems. And that needs to be figured out. And then we got to find out why this destroyed $250 worth of Raspberry Pi 4s. Why? So he's taking the 12 volts and he's trying to develop 5 volts here, and then he routes it all the way around the board to the Raspberry Pi, which is right next to the power amplifier low pass filters. So do we need some shielding? Do we need to have filtering at this end of the line? Do we need to do the conversion to 5 volts here? I'm not powering this thing ever again from that power supply until I figure out what's going on. I'm going to run it from external 5-volt supplies. So there's just a lot of stuff here that needs a little more work. And then I think it's going to be an absolutely amazing radio, because pretty soon the processing power needed to run this radio be $20. Once they quit screwing with our supply chain and let Moore's law take effect for another year or so. And this stuff is the price of a micro-Sbitx. This stuff is cheap. And so when that stuff gets to be cheap, this is going to be an amazing radio. And it's almost full break-in. For a Morse code guy, this is like heaven. You are not scared every second that stupid relay is going to click back out and your next dit's not going to get heard while that relay clicks back in. You just sit there and send. And it doesn't come back between DITs because he has 100 millisecond minimum delay to allow the FIR filters and everything to operate. But instantly between letters, you're listening. It's effortless. It is so amazing. It makes the 7300 look like trash. So I'm hoping that we're able to fix this piece of equipment and get it to where it's a real product. The next version, which he is trying to rush to market, I'm like, please fix these problems first, is going to be much skinnier and it looks a lot more like a 705 at half the price. But we've got, in my opinion, we've got some real manufacturing issues that need to be solved because people are going to tinker with this radio. And most people don't have a Siglent spectrum analyzer to actually look at the output and see if they've damaged something or if it's suddenly non-legal. And we really can't afford to have our radio waves be crabbed up with a bunch of signals that are all over the federal spectrum. So that's what I got, and I'm open for questions. Yes.
If we buy one of these, should we consider it a full-time job?
Well, he only sold, I thought he sold 500, but he actually only sold 150 of the developers edition. And Asher was very honest. Everybody knew what they were getting in for. This is like putting your money in a get rich quick scheme. You know, this may not work. But I was so fascinated with this radio because I saw the potential of what I could do. And at that point, he didn't even have the TR switch. That's like gravy when that came up. So his next version, when it comes out, I suspect the market is going to force him to have a really sharp radio, which eventually the Micro-Bit X6 was a pretty good radio. His later versions are always pretty good radios because there's so much crowd input from so many hams pointing out, oh, but I tried this and boom, it quit working. And he has the advantage of that input. Yes.
How about a cheaper Raspberry Pi?
So what I'm going to do is I'm going to buy a $59 3A plus, which is about the cheapest you can buy. It's only worth $20, but because of the government, they're now 59.
Yeah.
But I can get one of those.
Okay, I'm thinking like a Pico for $4.
You have to have the floating point unit. I think the Picos may not have it.
I think it does.
And you may need more RAM. Nobody knows the answers. And then you've got to find the libraries and recompile. I compiled several times because I made multiple changes to his code. His first code did not put up the proper transmit frequency in Morse code. So I fixed
Pico
that.
may not have the visual capabilities to run like the display that the full pipe does.
Well,
That may be also the.
I'm not interested in the built-in FT8 and the built-in. I don't care about that. What I care about is a radio that's clean and has full break-in.
But you could add that to that Raspberry Pi later if you.
Oh, yeah. Well, if I get the darn thing to work again, you know,
You can buy a Raspberry Pi.
this was the coolest radio I've owned in 40 years when it worked.
All right,
One thing I did notice.
folks, thank you very much, Gordon. All right, we're going to, if there's no questions, I don't see any here, I think on the, okay, we're going to go ahead and cut this presentation.